going to school? School's fun, buddy. It's fun to go to school.
I want to put the apple.
And guess what? We got your new dinosaur hat in. Look, you wear your dinosaur hat?
Minutes. All right, let's go over how to do this. So again, you got to use a quadratic formula. X is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. A, B, C. So if we plug in, we get x is equal to negative 14 plus or minus the square root of 14 squared minus 4 times 8 times 9 all over 2 times 8. And then you use a calculator to find out what the, what's it called, the radicand, the part under the square root is. So if you do 14 squared minus 4 times 8 times 9, you get negative 92. And then and the denominator, 2 times 8 is 16. Now this is the part where in the past you may have just said that, okay, I can't square root negative 92. That means no solution. But now we know better. That means we just have a complex solution. So I need to look for, like we were doing last week, the things I can square root and pull those out of the denominator. So I can square root 4, and 4 goes into 92 23 times. So 4 times 93. And I can square root negative 1. So if I factor out the 4 and the negative, oh, why did I write 93? 23. 23 over 16. All right, and then I'll go ahead and actually do these square roots. So I'll get negative 14 plus or minus, the square root of 4 is 2, square root of 23. I can't, it's a prime number. There's no perfect squares that factor into it, and I can't square root it without getting a decimal. So I just leave it as the square root of 23. And then the square root of negative 1 is I over 16. And then there's one last thing that you should do. You should notice that all 3 of your terms are divisible by 2. So you should reduce this to negative 7 plus or minus the square root of 23i over 8. So this quadratic has 2 complex solutions, negative 7 plus the square root of 23i over 8, and negative 7 minus the square root of 23i over 8. Questions about this problem? This is the task that I asked you to do on your own from yesterday. Or I guess that would have been from Monday's class. Do we feel like we're okay with this? Or do you want to see another? All right. I'm not getting any issues, so I guess we'll move on. All right, here's what we're learning about today. We're going to use the fundamental theorem of algebra to determine the number of zeros. That's super easy. Finding all zeros, I mean, we've already done. And then finding conjugate pairs is super easy. We've actually already done that. So really the only new thing we're doing is here, and it's just super, like, really, really easy. All right, so let's start out with it. subpoint B in your notes is the fundamental theorem of algebra. What it states is that if f of x has degree n, then you have at least, and n is greater than 0, then you have at least one 0 that may or may not be complex. I should say it's got to be complex, but it may or may not have an imaginary part. So basically, this is telling us if our function has degree like x to the first or any number higher than that, x squared, x to the third, x to the fourth, then it has a 0. And that 0 could be a real number, or it could be a real part plus an imaginary part. It could be a complex number. The second point is the real big one, the linear factorization theorem, which states that if your polynomial has degree n, then it has n linear factors and n complex zeros. So for example, f of x equals x cubed has 3 linear factors and 3 complex zeros. What I mean by a linear factor is a linear factor, you don't have to write this down unless you want to. A linear factor is x to the first plus or some constant or minus some constant. Note that there's a distinction here. Because these are complex zeros, they may not be x-intercepts. X-intercepts only occur on the real zeros. Your, like 2 plus 3i, if that's a 0 of your function, or like the one we just did before, that quadratic, which had, what, -7 plus or minus the square root of 23i over 8, those zeros are not x-intercepts because that parabola actually opens up above the x-axis. It never intersects the x-axis. All right, I'll give you a minute to write all this stuff. Really, once you're done writing this, there's not a lot more notes after this. Mostly just examples and practice. I have to teach from home today to keep an eye on my dog. She just had surgery to get a lymphoma. Oh, we just got people. There we go. All right. Okay. Yeah, so I have to make sure she's not licking her surgery site. All right, how are we doing? Does anybody need more time?
Maybe a little bit more time.
Yes.
A little bit, a little bit. Okay. So the perks of teaching from home is I get to, brew my own coffee. Consequence though is I don't think my Wi-Fi is good enough to, or stable enough to use the webcam. All right, how about now? More time still? All right. Okay, let's do it. I'm excited. So for example, let's look at these following functions and identify their degree and then how many zeros that means they have. For the first one, its highest power is x to the first. So this has a degree of 1. What you barking for? Go get him. Go get it. There's your good shiny bunny. So it has degree 1, which means it has 1 complex 0. And we can find out what that 0 is. If we set this equal to 0, we get x is 2. So this has 1 complex 0. It happens to be a real 0. So this is also an x-intercept. Its degree of 1, it has 1 complex 0. That 0 is x equals 2, which is also an x-intercept. For B, its highest degree is 2. Which means it must have 2 complex zeros. If we set this equal to 0 to find out what they are, no parentheses. we could do that by, I believe for this one, we could factor or do the quadratic formula. And since it is factorable, I'm going to go ahead and do that. This would be x minus 3 squared. Negative 3 times negative 3 is positive 9. Negative 3 plus negative 3 is negative 6. So this has two zeros, x equals 3 and x equals 3. Or you can say that it zeros, it has, or not, it has a 0 of 3 with multiplicity 2. Right? Which reaffirms what we learned like a few weeks ago, that this power here tells us the multiplicity of this 0. And both of these zeros are x-intercepts. So this has one x-intercept, x equals 3. Degree 2, two complex zeros. It has one x-intercept. Or you could think it has an x-intercept with multiplicity 2. It has one unique x-intercept. And that kind of distinction, I don't know, messes people up sometimes. You might say, Mr. Like, no, this only has 1 0. The 0 is x equals 3. It doesn't have 2. But it does, right, because of this power. This linear factor occurs 2 times in the problem. So we say that it has 2 zeros. That might just be semantics, but that's what they agreed on, I suppose. All right, last one. This one has a degree that its highest power is 3. So it must have 3 complex zeros. Oh gosh. To find out what they are, again, we set this equal to 0. Whenever you try to solve a polynomial with a degree higher than 2, you should always try to factor. For this one, it looks like I can factor out x, which would leave me with x squared plus 4. And now that I have this down to a linear factor and a quadratic factor, I can separate these and set them both equal to 0. So I have x equals 0. That's one of them. It's an x-intercept. And I have x squared plus 4 equals 0. Which means if I subtract 4 from both sides, x squared is equal to negative 4. And if I square root, then x is equal to 2i and negative 2i. So again, that gives me my 3 zeros, 2i and negative 2i. These zeros are not x-intercepts because they're not real numbers. So again, it does have 3 zeros. 2 of them are not real. 1 of them is real. The real one is your x-intercept. All right, any questions about that? Any concerns? Does anybody need more time to write? Okay. It's your turn then. Tell me how many zeros this function has. And then if you can find out what the zeros are, that would be great. I'll give you 1 minute. But in Pear Deck, all I want is how many zeros does it have? That's it. Just how many complex zeros. You should, on your own, see if you can find out what all of them are. All right. As you can see, it's got 5 zeros. We are pretty good with that. Because again, it's just based on its degree. That's all there is to it. This polynomial has a degree of 5, so it has 5 complex zeros. To find out what they are, if we cared to, I would factor. It looks like these two have x cubed in common. If I factor that out, I'm left with x squared plus 9, which means I have x cubed equals 0, or x squared plus 9 equals 0, which means x equals 0 with multiplicity 3. And again, this right here is an x-intercept over, for my quadratic, I would subtract 9. X squared would equal -9. Square root both sides. X would equal plus or minus 3i. And so that gives me my two other zeros, 3i and -3i. Those zeros, since they are not real, are not x-intercepts. See, I told you it wasn't going to be that bad. The only new thing in today's class is just looking at the degree and determining the number of zeros. This, hopefully, we already knew how to do coming into here. All right. The last thing we're going to talk about is conjugate pairs, at least I think. Oh, there's some more example problems, I suppose, that we can do. Okay, here's the rule. It's actually a pretty useful rule. If f is a polynomial function and a plus bi is a 0, then a minus bi is also a 0. Note that b cannot equal 0. So basically, if you have a 0 that's not an x-intercept, if you have a non-real 0, its conjugate is also a non-real 0. Which hopefully should make sense to you. The way we get those non-real zeros is by square rooting negative numbers. But every time you square root to solve a polynomial, you have to take the plus and minus square root, right? So what that means is that it's impossible to have just one non-real 0. That would mean you forgot to do the plus and minus square root. Every non-real 0 has a pair to it, which is the opposite sign, plus or minus. Isn't that just dandy? All right, anybody need more time to write? All right, cool. All right, so for example, what that allows you to do is some pretty powerful math. Let's say I want to create a 4th degree polynomial with real coefficients as these zeros. Well, I know since it is a 4th degree polynomial, it should have 4 complex zeros. But they only give me 3. Or do they? Bum, bum, ba. If 3i is a 0, which you could write as 0 plus 3i, if you want to think of it like that, then 0 minus 3i must also be a 0. So negative 3i is a 0, and now I have 1, 2, 3, 4. I have all 4 complex zeros that I'm supposed to have. So I can write my function as x plus 1, x minus 1, x minus 3i, and x plus 3i. So we just write our function as a series of linear factors. Again, how I made these is just doing the opposite signs on all of these. If I want negative 1 to be 0, then I would have to have my factor as x plus 1. That way, if I plug in negative 1 plus 1 is 0. I'm pretty sure, I think I checked this in WebAssign. Tell me if I'm wrong. But I believe if you type this in, it will count it correct. If you want, you could multiply this out. I'm going to go ahead and do that once, and then I don't think I'm ever going to do it again. X times x would be x squared. X times negative 1 is negative x. Positive x times, or 1 times x is positive x, so those will cancel out. 1 times 1 is negative 1. Over here, x times x is x squared. And again, I get positive 3ix and negative 3ix, so those cancel out. Negative 3i times positive 3i will be negative 9i squared. But I squared is really negative 1, so this becomes positive 9. Oh, no. Too much. Ah! Just wanted to make room. Okay, now we multiply it out again. X squared times x squared is x to the 4th plus 9x squared minus x squared minus 9, which is equal to x to the 4th plus 8x squared minus 9. There you go. But again, I don't think you actually have to go through this process when you're doing it in WebAssign. I think that first answer where we just put 4 linear factors in parentheses will be accepted. And I'll accept it on a quiz or test. So again, if we took a test on this and it doesn't accept it, but you know that you're right, when I manually grade it, I'll give you those points back. You just won't get that green reassuring check mark. All right, questions about this, or does anybody need more time to write? All right. Your turn. Find a cubic polynomial with real coefficients that has 2 and 1 minus I as zeros. All right, it looks like the answers I got on Pear Deck are right. Though there might be some sign issues. So since 1 minus I is 0, then 1 plus I must be a 0 too. Again, since this is a cubic, that means it has 3 zeros. And I've got 1, 2, 3. So then I can write this as x minus 2, x minus 1 minus I, and x minus 1 plus I, which you could simplify to x minus 2 times x minus 1 plus I, and x minus 1 minus I, if you distribute the negatives. And again, if you would like to multiply this out, feel free. But I believe you could just leave your answer like that. And to be honest, I don't really know if there's much value in multiplying it out. I think it's more useful in this form because then we can see what each zero is just by looking at it. All right. Oh, I know why I was going to go over these. Okay. Yeah, there's some tricks I wanted to show you. All right. So for this one, there is a trick to solving this quartic. You could attempt to solve this by doing the rational zero test and looking for the rational zeros that you can divide into this. However, there's a trick where you won't need to do that or use a calculator. You can do this by hand a little quickly if you notice that this has what we would call quadratic form. Right? It's of the form ax squared plus bx plus c, with the only change is that our powers are doubled. And since that's the only change, we can use all of our techniques for solving a quadratic. So I could factor this by saying what two numbers multiply to be negative 20 and add to be negative 1. That would be what? Negative 5 and 4? So I could factor this into x squared minus 5 and x squared plus 4. And you could check your work. X squared times x squared is x to the 4th. X squared times 4 is 4x squared. Negative 5 times x squared is negative 5x squared. Negative 5x squared combined with 4x squared is negative 1x squared. And then negative 5 times 4 is negative 20. And then we can solve these by setting them both equal to 0. X squared equals 5. X squared is negative 4. So x equals the square root of 5, the negative square root of 5, 2i, and negative 2i. So those are my 4 zeros. These two are my x-intercepts. So this function has 4 complex zeros and 2 x-intercepts. And it has 2 non-real zeros. I could have also done the quadratic formula with the following change. I could have done x squared is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then when you're solving it, you'll have an extra step at the end where you have to take the plus or minus square root of your answers. All right, questions about this? Actually, and I take that back. Now looking at our zeros, the rational zero test would absolutely fail this problem because it has no rational zeros. It has 2 radicals and 2 complex. That's a good thing I went over this. All right, questions on this one, or does anybody need more time to write? Okay. All right, then we'll do one more and then that'll end class. All right, let me show you another technique that you can use. So if I want to find the zeros of this quartic, given that this is a 0, I can do that by combining all the information that we just got. The first conclusion that I would make when trying to solve this problem is that since 1 plus 3i is a 0, that means 1 minus 3i is a 0 too. So that means x minus 1 plus 3i times x minus 1 minus 3i are 2 of my factors. If I multiply this out, get that. And then if I multiply it out further, x times x would be x squared. Negative x. Positive 3ix. Negative 1. Plus x. Or plus 1. All right, if I then combine like terms, x squared minus x minus 2x the plus 3ix cancels out with the minus 3ix. I've got this plus 1 here. Minus 3i cancels out with positive 3i. And then this is really positive 9. So I guess I can add that with the 1 to make 10. To get x squared minus 2x plus 10. And then I can use that factor to divide my polynomial and get the other quadratic, which I can then solve. Note that you would have to use long division since this is not an x plus c form. So I would do x squared minus 2x plus 10 and divide that or take negative x to the fourth minus x cubed plus 6x squared plus 2x minus 60 and divide that by the factor I got from my complex solutions. This is kind of a nasty problem. And then I'm confident that you know how to long divide. What you'll be left with is a quadratic, which you can then solve by factoring, or the quadratic formula. So those are two new techniques you can use to solve polynomial functions, given that we now know how many there are and that every complex number's conjugate is also a 0. All right, so it's 8:46. I'm going to do another one of these as bell work tomorrow. The homework is in WebAssign. If you get stuck WebAssign, read through the textbook if you want more examples, or if you want to finish out this example and you don't know how to long divide those, you can do that in WebAssign or in my own classroom notes. All right. Have a good one, everybody. If you have run into anything, email me, let me know, and I'll help you out. Bye.